So where we left off was the orbital diagram for fluorine. Again, we don't double up till we have to, and just by convention, up arrows are always first. So next we're going to consider nitrogen. This would be an incorrect orbital diagram. Place one unpaired electron in each orbital in the same energy level that all spin in the same direction before adding electrons that spin in the opposite direction. So here we doubled up before we have to. We have an open orbital energy level right here. So there should be an arrow here before we start doubling up. Now again, they could all be down arrows, but just by convention, up arrows are typically used first. By having one unpaired electron in each orbital, it creates a system that is at a lower energy level, and this is because of a physics thing. Not really something you have to explain the why of, but the reason Hund's rule is a thing is because it is a lower energy level, so that's why we don't double up until we have to. So the correct orbital diagram for nitrogen would be this, where we have single upward spins in each orbital before we actually double up. This does not violate Hund's rule, and we followed Aufbau's principle too by filling 1s and 2s before filling 2p. So for these subshells, n equals 1 contains one subshell, 1s. n equals 2 contains two subshells, 2s and 2p. 2s can hold 2 electrons, 2p can hold a maximum of 6 electrons, so altogether, n equals 2 can hold a max of 8 electrons. n equals 3 contains 3 subshells, 3s, 3p, and technically 3d, even though we don't fill 3d until after 4s. 3s can hold 2 electrons, 3p can hold 6 electrons, and 3d can hold 10 electrons. So as a whole, n equals 3 can hold a maximum of 18 electrons. If we go to the fourth energy level, we add on for F. F can hold 14 electrons. So max we have 14 plus 10 is 24, plus 6 is 30, plus 2 is 32. So n equals 4 can hold up to 32 electrons. Now we don't often get a problem where you have to write the electron configuration for something that contains an F orbital, but it's still something that you should definitely know how to do. It is fair game. So it could happen, but it doesn't happen often. If we consider shielding effect within a shell, the electron density in a nucleus is greater for 2s electrons compared to 2p electrons. So 2p electrons experience a greater shielding effect from the 1s electrons than the 2s electrons. So 2s electrons spend most of their time further from the nucleus than those in 2p. But the electrons in 2s have a higher probability of spending more time in close proximity to the nucleus than those in 2p. So this is going back to that computer model. If you remember, it would plot where electron could be 100% of the time and then 90% of the time, and that's where we get our quantum mechanical model. The S was a sphere shape. Okay, so that was the 90%. It could be found within the sphere. This sphere has a lot of space, if we consider the nucleus in the very center, a lot of space where an electron could be closer to the nucleus. If you consider the P shape, whether it's X, Y, or ZP, it had a peanut shape where it had like two circles, kind of like a figure 8. And if you consider the nucleus in the middle, the probability of an electron being closer to the nucleus in 2p is actually less because of its shape versus 2s. Okay, so S has a sphere, a lot of chances that you could be in the nucleus. P is a peanut shape, tight center, not much chance that you're really close to the nucleus. So that might be hard to wrap your brain around. But remember, 2s, or really any s electrons, is going to have a higher probability of spending more time in close proximity to the nucleus than those in a p shell. So because of this, the overall shielding effect, which is caused by the 1s, which is overall closer to the nucleus, is greater for 2p than it is for 2s. So 2p electrons are shielded more than 2s. Okay, and this kind of goes into that as well, pretty much the same stuff I just said. 2s spend their time much closer to nucleus than 2p, so 2p experience a greater shielding effect. Greater repulsive forces that the 2p experience from 1s result in a lower ionization energy for the 2p electrons. So it is easier to strip away an electron from 2p than 2s, even though they are both in the same energy level. In all shells, electron density near the nucleus decreases with each subsequent shell that is added. So the shielding effect increases for each subshell that is added. This kind of, again, goes into that. As subsequent subshells are added, the ionization energy decreases due to an increased shielding effect. So there's more shielding effect, more repulsion from other electrons. It's going to be easier to take an electron away, which is essentially ionization energy. So the more effectively the electrons within a subshell are able to penetrate the shielding electrons, the greater the ionization energy of those electrons. So less shielding means it's going to be harder to take it away. So here we have the ionization energy of 3D, which is less than that in 3p, which is less than that in 3s, because 3s experiences the least amount of shielding in these three shells that we are considering. So although the average distance between nucleus and electrons decreases as subshells are added, the ionization energy decreases because of the shielding effect. So even though the distance is getting smaller, you would probably expect it to be higher, but shielding effect is something that you also need to consider, not just the distance. And again, this is from Coulomb's law, comes up again and again. So Coulomb's law does not take into account shielding effect. So if there's something that you expect to go one way because of Coulomb's law and it doesn't, it's probably because of shielding effect. Okay? I think that's it for Unit 1.5. Let me know if you have any questions.